Last week we talked about what would a global social planner do about a problem like climate change. That provides sort of a useful yardstick in terms of efficiency and so on and so forth, but of course it's not a very realistic depiction of how climate policy is really made. So in the first hour before the break I'm going to talk about essentially game theory. I'm not going to go very deep or very detailed because I assume that you have seen the basics of this, so I'm going to highlight a few points that are specific to climate, a few things that you haven't seen before, and then after the break I'm going to talk about what actually happened during the international climate negotiations over the last 21 years. But I'll start with just a brief recast of where we were. So last week we talked about optimal climate policy and what you do if you want to maximize the problem. If you want to maximize welfare for a problem like climate change, essentially equating the marginal cost of emission reduction to the net present value of the marginal benefits. We did that, and then you find typically that you go for an interior solution that is very hard to defend a position where you're not reducing greenhouse gas emissions at all, but it's also very hard to defend a position where you reduce your emissions by 100%. We talked a bit about the numbers. I showed you the supply curve of greenhouse gas emission reduction, where on the vertical axis we're looking at the carbon tax that you could impose in the year 2015, and then on the horizontal axis concentration of greenhouse gases that by the end of the century that would result. And we also talked about how much we would be willing to pay to reduce greenhouse gas emissions at the margin, and that is displayed here. And if you put these two graphs together, then what we find is that yes, you would want to reduce emissions by a little bit, but not by a lot. So we talked about these things, and that particular result is displayed again here. We're now looking at 4 different scenarios. The line on top is the solution without any greenhouse gas emission reduction. That's the one given here. Then we have the situation here where we jointly reduce greenhouse gas emissions so as to maximize global welfare. So that's essentially the social planning solution. The results here are slightly different from what I showed last week. That is because we're looking at a different incarnation of essentially the same model developed by Bill Nordhaus, but here co-developed by Zili Yang. And at that time both were at Yale. Zili is now in Binghamton. So what we find is that no control versus optimal control. Yes, you want to reduce emissions, but nowhere near enough to stabilize greenhouse gas concentrations in the atmosphere, and therefore you're not going to stabilize the climate either. Now, this assumes a global social planner or a joint maximization of welfare, and essentially what you do there is you equate the cost, the marginal cost of emission reduction to the global total marginal damages of emission reduction. But the global total marginal is of course the sum of regional marginals, and here we see that split out for 16 regions, where the global total is $23 per ton of C, and that is of course a fairly arbitrary number, as you should realize by now. But the shares are of course also subject to great uncertainty, but not the fact that for any particular region or for any particular country, the damages that fall on the country itself or on the region itself are necessarily a fraction of the global total. So in a non-cooperative solution, what would you do? You would equate the marginal costs of emission reduction to the marginal benefits that fall on your own country, which is necessarily less than what would fall on the world as a whole, and that is shown here. And that explains the difference between the cooperative equilibrium, where you take into account the damages across the world, versus the non-cooperative equilibrium, where you only take into account the damages that fall on yourself, on your own country. And what you see is that the non-cooperative equilibrium leads to higher greenhouse gas concentrations in the atmosphere than the cooperative equilibrium. And this is exactly what you would expect. What you also note is that The non-cooperative equilibrium does not coincide with the no climate policy at all, because there would still be damages, right? And you would still incur some marginal damages on your own country, and particularly the larger countries like the US and China would actually see a considerable chunk of the global total falling on themselves, so they would be doing something about climate change. But it's considerably less than you would in the cooperative equilibrium. Yeah.
So is the reason why it's harder is just because essentially it means that countries is it just the externality effect of essentially countries that like suffer slightly less then end up polluting more than they would normally have because they don't take into account the
exactly. Exactly. The mechanism is very simple. In the cooperative solution, the USA would impose a carbon tax of $23. In the non-cooperative solution, the USA would impose a carbon tax that is 4% of $23. It is 8 cents, is that correct? So that is as simple as it gets. So a strong deviation between cooperative and non-cooperative. Now, that leads me to the second question. The cooperative solution necessarily maximizes global welfare, so that is the best we can get. Can we get to the cooperative solution in a world where there's no global dictator? The usual way of looking at this question is through the lens of free riding. And that, I think, is best understood with some simple example, a worked example. Free riding is a bit of a strange thing to do. Essentially what you do in free riding is your starting point of the analysis is to assume that there's a global coalition that everybody cooperates to, in this case, reduce emissions. And then one by one, every country that is part of the coalition wonders, should I continue to cooperate with the rest? Assuming that the rest will continue to cooperate with each other. That is essentially how free riding is defined. So everybody plays nice. I consider playing not nice, but I will assume that everybody else will continue to play nice. And is it then better for me to play not nice? That is essentially how free riding is defined. It's a bit of a peculiar definition. So what do you do? If you want to analyze free riding, let's assume that the cost of emission reduction for country I is a quadratic function, cost C is alpha, that's some parameter, unit cost, and then the emission reduction at R, and we make a quadratic function. And that just depends on what the country itself is doing. So Ci is a function of alpha I and Ri, but not of the other R's, the stuff that other countries are doing. The benefits of emission reduction, on the other hand, depend on what everybody else is doing. So the benefits, B, of emission reduction are specific to country I, and there's a country-specific constant there, beta I. But what matters is the relative emission reduction times the size of emissions. What matters is the sum total of all emission reductions across the world. So this is a classic public good problem. If you want to solve this non-cooperatively, then what you do is you equate marginal cost to marginal benefits. Basically, it's what are marginal cost and what are marginal benefits. Marginal cost, we see the R. That's simple. That's 2 alpha R. This costs only depend on what you do yourself. So that derivation is trivial. The marginal benefits, the VDR, take a bit more thought. Obviously, you have your beta pop up there, and then what you see here is you need to take the first partial derivative of this term here to emission reductions Ri. They are 0 everywhere, apart from your own country. The first partial derivative of Rj to Ri is 0, except when Ri is Ri, and then it's 1. So what remains of this summation here is E sub I. And then we have an optimal emission reduction, non-cooperative optimal emission reduction, that is beta I times EI over 2 alpha I. And that holds for all countries I. Right? That's the non-cooperative solution. The cooperative solution looks something as follows. Costs of emission reduction only depend on what you do yourself, so the CDR stays the same. But what you now need to do is you need to take essentially the derivative of the sum of all benefits to the action of country I. And what happens there is that, yes, you sort of affect yourself, but through your emissions you also affect all the others, and you have to essentially take into account the impact of your emissions on everybody else. That is what goes on here, and that becomes the sum of the betas, but weighted by your own emissions, EI. So that implies that optimal emission reduction in a cooperative case is very similar form, beta times EI over 2 alpha I, where beta is now the sum of the beta j's. So it looks very similar, right? We had beta I over EI, beta I times EI over 2 alpha I. Now we have beta EI over 2 alpha I. And the big difference is that the subscript disappears. So that is the cooperative solution versus the non-cooperative solution. Now the question of free riding, as I said, is one country considers what would happen to my costs and my benefits if I stop cooperating, but the rest continues to cooperate. So what is the difference in costs? Yeah, it's essentially cooperative costs minus non-cooperative costs, C prime minus C star. Cost function is alpha R squared. So you stick it in, we know R prime, we know R star, so we have beta squared, E squared over 4 alpha I. And the same thing here, but now we have the subscripts. So we can bring these two together, and really what you have there is beta squared minus beta I squared. That is the crucial cost difference. The difference in benefits is not beta prime minus beta star, because you assume that everybody else continues to cooperate. So their emissions don't change, but your emissions do. So that is beta double prime, or the benefits of that is beta double prime, and that is this expression here, beta I times Ri prime minus Ri star, but all the others continue to do the same, so there you have Rj prime minus Rj prime. That just drops out, right? So the only thing that matters is your own emissions, and then the difference between cooperative and non-cooperative behavior. And if you substitute the solution in, then what you find is that the difference in benefits is beta I times beta minus beta I.
What's the difference between the subscripts? What does the subscripts in this case mean if it's just beta I with no summation? It's just
beta I is the marginal damage or the marginal benefit in a particular country, whereas beta is the marginal benefit in all countries. So you can work this through. So this is beta times beta I, and this becomes beta I squared, just as we had there. So now the difference is we have a 4 here and a 2 here. And this sort of shows that it's always better to free ride. Let's just double check that. So we start with a situation where the global marginal is 4 and the national marginal is 1. So essentially we're considering a country that makes up a quarter of the world. So it's a fairly sizable country. We set alpha to 1/2, so that it's always 2 times alpha, so that becomes 1. We set emissions to 1. What does that imply? So what we want to do is 4 squared minus 1 squared is 15, right? Over 2. So that makes 7.5. That's the difference in cost. The difference in benefits is 1, that's easy, times 4 minus 1, that's 3. Remember, we don't have to divide by 2. So the difference in cost, the cost savings are 7.5, whatever unit we work in, whereas the additional damages that are incurred through free riding are free. So you improve your welfare by 7.5 and you reduce your welfare by 3, so you're 4.5 better off. So if you make up 1/4 of the world's damage, then you want to free ride. So let's play around with these numbers a little bit. Assume that we make up 1/10 of the world damage. So beta is 10, beta I is 1. What do we have? 100 squared minus 1 squared is 99 over 2 makes 49.5. Difference in benefits is 1, that's always easy, times 10 minus 1, that makes 9. So there, the net increase in well-being is 40.5. So the incentive to free ride has become stronger because you make up a smaller part of the world's impact. So smaller countries have a greater incentive to free ride on the coalition than larger countries. Now let's make the country bigger, right? Because making the country smaller just increases the incentives to free ride. Make the country bigger. So we now assume that the national damages are 1/2 of the global damages. Now they're really in China territory. 2, 1, so this is 4 minus 1 is 3 over 2 is 1.5. 1 times 2 minus 1 is 1. So even if you make up 1/2 of the global impacts at the margin, then you're still, the cost savings outweigh the additional damages that are incurred. So incentives to free ride are strong. If we have a world with 180 or 200 sovereign entities that can do whatever they want, and there's no global social planner, then it is in everybody's best interest to ignore their impacts on the rest. And the global coalition, the international agreement on greenhouse gas emission reduction, falls apart. Which suggests that of the 3 lines that are given here, no climate policy, cooperative climate policy, non-cooperative climate policy, the non-cooperative one is the more realistic prediction. Go ahead.
Are there cases in specific countries where it's not in their best interest to not cooperate, or is it literally every country is separately?
In the model I just set up, it's every country. Of course, you can work through the equations and find exceptions there, but you will have a hard time finding it.
Wouldn't all the countries then realise that because of the fact that it's all in their best interest to do that, but based on the assumption that no one else does it, from a game theory perspective, it wouldn't?
Free riding is the usual way we consider this, and the problem with free riding is that it assumes what is often described as NAS behavior, even though NAS have nothing to do with this, but it's often described as NAS behavior, and it is sort of a myopic way of looking at the world. I wonder whether or not I should leave the coalition, but I don't take into account what my departure would do to that coalition. And in that sense, it's myopic behavior, that you look one step ahead, but you don't consider how would others respond to that. Now, that is NAS behavior in the sense that NAS described this sort of behavior, but NAS also strongly argued that this only makes sense if you have an infinite amount of players who play in an equilibrium. And we don't have an infinite amount of players, which is not a crucial assumption, but we're also not playing in equilibrium because we're showing that the global coalition is not an equilibrium. So in that sense, it has nothing to do with NAS. This particular case, where the starting point is a global coalition, one country considers to leave, that's myopic behavior. That's how we normally look at free riding. You can also consider chew behavior. And in chew behavior, you assume that other players respond to your action. And that becomes much more realistic, right? It's much more, we're not just considering one move, but we're also considering the response to our move from the other players. That's chew behavior or far-sighted behavior. The mathematics gets complicated, and typically I would hesitate to do this at PhD level. It gets complicated. It does not affect the results. Essentially what you would then do is, not quite, but you can sort of see it well. We are comparing things to the situation and not where we consider everybody to continue to cooperate, but we see whether or not we compare our behavior to the situation where cooperation fails completely. That of course changes the calculus, particularly changes in this particular example, changes this calculus here. But still you would have a hard time finding real benefits. But then of course also sequencing becomes important, because it then depends whether the small countries leave first or the big countries leave first, and so on and so forth. So that gets mathematically very hairy. I was actually going to talk about a different situation altogether. two different situations altogether. So the contrast that we draw here is between full cooperation and full non-cooperation. Either everybody plays nice together, or everybody plays on their own. But there's of course also intermediate situations where some cooperate and some don't. The typical way of analyzing that is through cartel theory, developed by Jean d'Aspremont, in, as you may have guessed, a situation of firms colluding with each other to maximize their benefits, rather than an international environmental game or international environmental agreements. D'Aspremont defines a stable cartel or a stable coalition as follows. A coalition is said to be stable if it satisfies three criteria. One, it has to be profitable. That is, for everybody who is in a coalition, that coalition has to, each of its members, deliver a welfare or a payoff that is greater than full non-cooperative solution, than the Nasdaq equilibrium. So that is profitability, according to d'Aspremont. Cartels have to be internally stable. That is, none of the players would like to leave. Nobody improves their welfare by leaving a coalition. And they have to be externally stable. And that means that nobody who is not in the coalition could improve their welfare by joining. And if all three conditions are met, then we say that the coalition is stable. The grand coalition, where everybody cooperates, is necessarily externally stable, because there's nobody who can join, because there's nobody left who hasn't joined already. For a coalition with two players, profitability and internal stability coincide, because the alternative for a two-player coalition is when somebody leaves, is that you essentially go to no coalitions at all. This only works for, and I'll get back to that, if there's one possible coalition only. That is cartel stability. Now, how does this work? Or rather, how does this not work? So let's go back to our work example. So I'm just going to consider two players who decide whether or not they want to cooperate with each other. And in the case of three players and four players follows automatically. So the cost of emission reduction for player one is still the function that we saw before, C alpha r squared. Benefits of emission reduction are now a bit simple because we can do away with the summation sign and just write it out. So the benefits are your unit benefit, then times your emission reduction effort and the other person's emission reduction effort. Non-cooperative solution is still the same. That's R and then beta 1, E1 over 2 alpha. And the same for player 2. The cooperative solution, where you maximize joint welfare, so you set the joint costs at the margin equal to the joint benefits. But C2 does not depend on R1, so that is still 2 alpha R1. And now, of course, this thing depends on both. So what we previously called beta, and that was the sum of all the betas, is now explicitly written out as beta 1 plus beta 2. And this is then your cooperative emission reduction. So essentially what you do, we go back to the non-cooperative solution. That is beta 1 times E1 over 2 alpha 1. The cooperative solution is beta 1 plus beta 2 times E1 over 2 alpha 1. So the difference between cooperation and non-cooperation is that it's the beta 2. So essentially what you do when you're joining the coalition with somebody else is you say, I'm going to reduce my emissions by more because I now take into account what my emissions do to you, to your payoff or your wealth. Now why do I do that? Because player 2 also increases emission reduction effort by beta 1. So I do more, and in return you do more. That is the deal that we're striking here. That is coalition formation between two players. And that works, and you can work out the difference in costs, that works out the difference in benefits. This works if this pays off to you. If my extra emission reduction on your behalf brings a small cost to me, whereas your emission reduction on my behalf, your extra emission reduction on my behalf, brings a large benefit to me. In that case, this is a good deal for me. So what I want, I'm willing to join in a coalition with you if my increase in costs is small. My increase in costs, because I consider your well-being, is small relative to my benefit, because you now take my impact into account. So that is reason from my perspective, right? I want to do a little bit more so that you will do a lot more. But if the reason is from your perspective, then you have exactly the opposite demand. You want to do a little bit extra in the hope that I would do a lot extra. So this is the condition for player 1 to join the coalition, and this is the condition for player 2 to join the coalition. And they are the exact opposite of each other. We both hope to do a little bit extra so that you will do a lot more. And you would hope that I would do you would do a little extra so that I would do a lot more. You see what is going on here, right? It is hard to meet both conditions simultaneously. The negotiation space is pretty small. This is for a 2-player coalition. Of course, if we consider a 3-player coalition, then what we would have is that we would say, well, this condition also has to hold for player 3, and delta C3 should be smaller than delta B3. And the same for 4 and 5 and whatever. And you immediately understand that there is not a lot to play with. And in a way you can see this as barter trades, and this is essentially just a logical depiction of the Edgeworth box that you may recall from way back when. That is essentially what is going on. Strictly barter trade, there's no productive economy behind, so welfare gains are small. And the implication of this, and this was first written up by fellow Carrara with a bit of help of Domenico Siniscalco, and by a bit later, a bit more formalized, a bit more explicit by Scott Barrett. The implication of this, we have to meet all these conditions, is that the cartels that are formed have one of 2 characteristics. Either they are small, that is, only a few players want to cooperate with each other, and because only a few players switch from cooperative to non-cooperative to cooperative behavior, emission reductions would not fall by a lot. Emissions would not fall by a lot. Emission reductions would not increase by a lot. So that is one way of satisfying all these conditions. And the other way of satisfying these conditions is that the additional emission reductions from cooperation are small. So either the coalition is small in the sense that it has few members, or the coalition is shallow in the sense that it doesn't do a lot. There are a lot of people cooperating, but they don't promise to do more than they otherwise would have had in a non-cooperative solution. That is for one coalition. Non-cooperative solution, everybody only cares about themselves. Full cooperation, everybody cares about everybody else, and then there's this intermediate situation where a few of the many players join forces, but in one coalition only. So you can ask the question, what happens if you have multiple coalitions? If you have multiple small coalitions? The way to understand this, I think, is to assume that these coalitions are formed sequentially. First we form one coalition, then we form another coalition, then we form a third coalition. In reality, of course, this would be done in parallel, but it's much easier to understand in sequence. So the starting point is that there's a large number of players, and then we know from Carraro and Barrett that most likely a small number of them would form a coalition. So what does that mean for the remaining players? Say we start with 180 countries and then 5 of them form a coalition, then the remaining players are left in a situation where there's 175 players. Not a lot has changed. So they would form a small coalition again, because the base situation hasn't changed. It does matter if you start with 10 players and 5 of them form a coalition, then things have materially changed for the remaining 5. But if you start with 200 players and 5 form a coalition, then nothing much has changed for the remaining. What I'm going to say only holds for large number of players. Start with a large number of players, a small fraction forms a coalition, nothing much has changed for the remaining players, who then you would think would form a small coalition again. Second coalition is formed. But then what happens is that you need to add a condition to cartel formation. thus Permon's definition of stability is no longer sufficient. It's no longer the case that you need to be profitable, internally stable and externally stable. You also need to be intercoalitionally stable. That is, members of coalition A do not want to join coalition B, and members of coalition B do not want to join coalition A. So you add 2 constraints to your allocation problem, and then if you add a third coalition, you add 6 constraints to your problem, because A does not want to join B, does not want to join C, B does not want to join A, does not want to join C, and C does not want to join A, does not want to join B. That's 6 conditions that you need to add. And then if you go to 4 coalitions, you go to 12 such conditions. It's n times n minus 1. And so what does this imply? That if you have a large number of small coalitions, then you impose so many constraints on your behavior that you cannot find a solution anymore. Essentially, the number of variables that you want to solve stays the same, but the number of equations that it describes grows quadratic. So you have 200 players. You cannot have if you have 100 coalitions, or if you have 50 coalitions, right? You have 50 coalitions, then you have more than 2,000 conditions that you need to meet. But with 200 degrees of freedom, you're never going to get there. It's just completely impossible. So because of this, the number of small coalitions is necessarily small, which means that if you start with a large number of players, then adding a second coalition and a third coalition would reduce emissions a little bit, but you very quickly run out of the number of coalitions that you can possibly form in a stable way, and therefore adding multiple coalitions will not change the picture, the basic picture of Carraro and Barrett, that this intermediate form of partial cooperation will simply not do a lot for your emission reductions either.